a quick presentation, first of all, and then we will actually dive into the software and go through all the various features and functionality. Once we have concluded the demonstration of the software itself, then we will give some time to the forum for questions and answers, so you can save your queries until then. Overview of RBLX. RBLX is a fully quantitative RBI software that rates current and future risks and recommends inspection plans. The following equipment is covered by RBLX. So we're covering pressure vessels, pipelines, storage tanks, heat exchangers, pipe work, and pressure relief devices, also known as PRDs. The main features of the software application is that it's user-friendly. It's very intuitive interface, which you'll understand when we walk through it. So we don't need to go through any kind of exhaustive training process. It's quite intuitive, and the workflow of going from one end of the system to the other is fairly straightforward. It's a fully quantitative approach and includes a rapid qualitative damage screening. We have one of the latest technologies behind this software suite. It's a web-based application using web technologies which adapt to both desktop, laptop, and tablet devices. So in fact, you can use all the functionality in the software on a multitude of devices, and it's also mobile capable as well. We're analyzing over 25 metal loss corrosion mechanisms, and we have 15 metal loss models included in the application. And we analyze over 45 non-metal loss damage mechanisms, including SCC, mechanical, metallurgical, external, etc. We then look at the inspection history that's recorded in the system, and then we are able to calculate current and future risks. And we also take into account the tolerable risk level of that's specified, and it varies from client to client. The inspection plans are auditable, and we have facility to store all the documents in a library in the system, so we've got full document management capability in the system. The system supports multi-cultures, multi-languages. We have the facility to upload the data via an Excel import mechanism, and we also have the ability to export all the data to Excel as well for further analysis. The process that we follow in RBLX is the following diagram. So we start with the data gathering phase, moving into inspection history analysis. Then we look at the metal loss. Then we look at the non-metal loss analysis. At the end of all that, we come out with a probability of failure for the metal loss and all the different non-metal loss damage mechanisms. We finally then analyze the consequence of failure, taking that consequence and probability together to work out our risk. Current risk, that is, and then we look at what the future risk looks like in order to determine our inspection plan. And once we've done the inspection plan, obviously the inspection is then executed and the whole process is repeated once again. So I'll now proceed to demonstrate to you the actual software application itself. So the landing screen of the RBLX system is one which has a menu on the left-hand side and a summary of all the facilities, units, systems, equipment, and component that we currently have specified in our database, and it will be unique to each client. So looking at facilities, we have a list of facilities coming in here with sample company names, recording its location, its name, and its type, whether it's a platform, if it's a chemical refinery, we record that there. Looking at the units, each facility has a number of units. So looking at facility A, for example, you can see all the units in there, and in platform B, you can see the units in there and their descriptions. And we also record the people per square meter value for that unit. You further break down the unit into a number of systems. So if we take one of those units, for example, this process one here, then we have two produced fluid systems specified here. We've got this liquid methanol storage. We've got variation of systems underneath those units, each with. Within those systems, we have a series of equipment. So if we look at the process liquid system, inside there you can see the tags for the equipment, the plant equipment types, so whether it's a pipe, atmospheric tank, vessel, heat exchanger, and then a description that goes along with that as well. We will come back to the equipment later on to work out the inspection plan, but this is the overview of all the equipment that we have. Just to highlight a point here, all of the data within the data grids in this application are sortable, filterable, etc. So if I wanted to do a query on this data here and I wanted to say, okay, starts with, or say contains vessel, I want to look at just the equipment type of vessel only, then I can filter away and it will filter the grid appropriately. And I can do that on each of those columns, and I can also sort them in a similar manner. These are all pre-grouped, so I can flatten out the grouping by removing the groupings here, and then we get a flat list, and I can look at the data just as a master list of equipment, if you like. So we've got a lot of interactive tools within the data grids themselves that allow us to filter the data and organize it in the way that we want to see it. Finally, the final level in the chain is the components. So for the component level, we have a set of components for each equipment there. So the one we are going to look at here is this vessel monopart component type, which is a drum of the equipment tag 20PB02AR. So I'm just going to jump into this component. This is where really all the data is residing in the RBLX system. So inside the component, we have a variety of sections at the top, with which I'm going to go through stage by stage. And this is what we meant by, in the earlier part of the presentation, about the fluid process of using RBLX. There's an actual proper workflow going from one end to the other. So at the moment, we are in the data tab, of which is split into 3 sections. So we've got in process. So in design installation, we first specify which equipment this component is linked to. So we select the equipment from this list that we have, and we already looked at that equipment list previously. What type of component this is, so we already highlighted it was a vessel monopart. And then we select the type from here as well. Then we give it a general description. So this is a first stage separator. We will then identify the drawing numbers here, PFD, PID, and other drawing numbers if we have them. Then we'd identify the commissioning date, and the RBI calculation date, of which is pertinent to all of our calculations. And then we specify design life years, of which once we specify this, the component life years and the remaining life years is automatically worked out for us and displayed there. You'll notice a number of calculated fields throughout the application. They're non-editable. They're just displayed there so the user is aware of what that calculated value is. Then we specify the external coating installation date, of which defaults initially to the commissioning date, but the user has the option to change it. Then we identify the material. So this is carbon steel A516. If I want to select some material, I can bring up this window here, and I have a whole host of materials that I can select from, each with their own properties, of which RBLX takes into account in its calculations. We've got quite an exhaustive list there, of which you can filter again, similar to what we saw on the equipment view. So once you select the material, then you specify your design pressure, and it's in bar, design temperature in degrees, and the minimum design temperature there as well. Then it's for us, based on the material that we've selected, they'll work out what the allowable stress is and the SMYS yield. But we can also override that by ticking this box and actually specifying our own values in there. So either you go with the values as forward based on the material, or you can override and specify your own. You then specify the size and diameter in inches. So we have this over 20 option, which we then put in our own value in there just now, and that's worked out from inches into millimeters for us automatically. The nominal thickness, again, you can either trust the value that's come through, or you can override it. In this case, it's been overridden, and we have 13 millimeters there. Then what's worked out for us automatically is the outside diameter, the inside diameter, and then we specify our safety factor here. We then select the design code, of which we have the following options. And then we indicate whether we have post-weld heated treatment or not, or whether it's heat traced by checking or unchecking these boxes. We identify the atmosphere that the component is sitting in for corrosivity. So this is offshore. We identify the joint efficiency between 0 and 1. And then we have further options like internal cladding or internal lining, or whether or not it's insulated. So the insulation has promoted further options in this scenario. So if I take this off, these are hidden. But if I select insulated, then I have to specify insulation type, and other insulation that may be present as well. So there's quite a bit of data just in design installation alone. Then we move into operating and process, where we specify the operating temperature in degrees, and it gives us the corresponding Fahrenheit and Kelvins out there. We indicate whether or not this component can operate at or below the MDMT, and then we give it the operating pressure, and again, it gives us the calculated PSIA and KPA values for us. We identify the flow velocity and the inhibitor efficiency. So this is all, these factors are being taken into account later on in the calculations. We have to ensure that all of the data is correct, obviously. Finally, we get to the operating fluid. You give the fluid a name. You can type anything you like in here, just identify the fluid and some description that's suitable. But from a master list here, of which is searchable. So this one is currently staged for me. Drop down the list and allow me to look through all the fluids that are available. When you select the fluid, there's a bunch of properties that are pulled in the background that influences some of the calculations relating to consequence. So we've got all this data in the back end here. You identify the operational fluid phase, either liquid or gas. You then identify the component fluid mass in kilograms and the component group fluid mass as well. You then would select the fluid release reduction safety system effectiveness, and this again will have some impact on the calculations. Sorry, just to go through that, that's from very low up to very high. The same for your fire reduction safety system effectiveness. Again, you identify how effective your fire reduction safety system is. You indicate the pH value, and then you've got a series of checkboxes in terms of the properties of the contents. So do we have water? Do we have H2S? Do we have CO2? Do you have H2SO4, etc., etc.? So there's a bunch of properties that we identify here, and leading us down to the toxic fractions. So we've got fractions identified here, giving us a overall toxic mass fraction at the foot here, which is calculated for us. So all this information is provided as part of the contents and the process of this. Finally, we go to inspection. Inspection has got a series of sections in there. We have internal inspection. So in internal inspection, you identify how many internal inspections have been done to date and the last internal visual inspection date. So here's the first 2010. And it works out obviously for you the number of service years since the last internal inspection on the end here. You then may or may not indicate if you've got lining and lining quality. If there are internal cracks, you would tick using this, and you identify the internal corrosion finding capability as well. For the inspection history itself, you would add a new entry in to the history box below, identifying what the method was, the date that the inspection was carried out, what the lining quality was, the general condition of and the crack finding capability that you had. So similar to the option that we had up here, but this is just for the historic ones, and any comments there as well. There is an overall summary at the bottom for all the inspections, by the way, which is just free text entry for someone to just summarize the overall perspective of the inspection of this component. Moving into external inspection, it's very much similar to the internal, just some different options there. Obviously, it's the last external visual inspection date. We've got external coating quality, of which you've got the following options, and the user would select from that. You're talking more about external crack finding capability and external corrosion finding capability, and you'll identify the insulation condition as well. Again, we've got an separate external inspection history here, of which similar values are recorded for each of those dates that you see there in chronological order. Then we have the thickness data. So first of all, by checking the first box, wall thickness reading, we indicate whether we have a wall thickness reading or not. Then we start to identify the data for wall thickness. So what we have there is identifying the current thickness check date, and then we specify what the current thickness reading is. We specify the previous thickness check date and the previous thickness reading. From that calculations and from the nominal thickness that we pulled through before, we've got calculated for us the minimal allowable wall thickness, of which can be overridden with this value here. So we're using the calculated value, but if we wanted to override that, and then what's worked out for us is the actual. And then finally, we've got the long-term corrosion rate, millimeters per year, and we've got the short-term corrosion rate, millimeters per year, of which the maximum is taken, and is 0.29 in this situation. So that is our result for our UT. Then once we've got all of our, this is still in the data section, once we've got all of our data ready, then we can make our way to doing our various analysis. So moving into metal loss, we have a summary page in metal loss, which basically identifies all of the corrosion rates that have been assessed for this component. What is summarized for us at the top is that we have this corrosion rate based on last UT reading. So you remember the 0.29 that we had in the UT reading is carried over here. We give a weighting to that thickness reading to affect our overall combined corrosion rate. So based on how I affect this value, this would indicate a change in the, so if I give this less weighting, then you can see the combined corrosion rate is more influenced by the theoretical models than the UT. So that real time updates that, and this is apparent throughout the application. Anytime I update a value, real time we can see the result in any calculated value. You don't have to press any run button or any calculate button. It all happens real time. So looking down here, we've got our sour water corrosion here worked out for us at 0.13, and we've got CO2 corrosion. Now, the way this is worked out is what's been applicable. Because we identified it back in data operating that we had a CO2 water H2S, then this is determined that these two models are applicable. And within the CO2 corrosion model, we have further inputs. So we've got water content, CO2 mole percentage, the viscosity, and then from that, it works out for us a corrosion rate. This our water corrosion one is just a pure calculation, so that doesn't have any additional inputs. But these models will have inputs in addition to what we already have input in the data section for it to work out the overall corrosion rate. So the sour water corrosion rate and the CO2 corrosion rate is combined to give us the maximum corrosion rate 0.35. With the weighting into account, we have a overall combined corrosion rate of 0.31. If we want to, we can override any of these models. So even if they weren't applicable by definition, we could put our own corrosion rates in here and override this theoretical model, and they will be taken into account in the combined corrosion rates. So if I was to put one in here, then we get an overall 0.5 influenced by my change there. So again, real-time updates on the interface. Then we move away from metal loss into non-metal loss. So the non-metal loss damage mechanisms are split up into 5 major categories. We have environment-assisted cracking, of which we have the following analysis being carried out. This summary is slightly different from the metal loss one, whereby, again, based on the data we provided in the design, installation, and the operating values, it decides which of these cracking mechanisms are applicable. So at the moment, we've got, as you can see, sulfide stress cracking and H2S cracking here. You can override that stuff by ticking these boxes. We can say, okay, even though the theoretical model didn't say that we should analyze these, we want to analyze them anyway. So we can tick these boxes and override this. The same applies for the mechanical damage. We just have different damage mechanisms in mechanical and metallurgical. You can see there's a range of metallurgicals in there. We've got our 4 external damage mechanisms from CUI ferritic to CUI-SS, and external ferritic and external SS. And then we have all these other damage mechanisms as well. So when it's been determined which of these mechanisms is the CUI ferritic external damage and the 2 cracking damages, sulfide stress cracking and H2S cracking, we then go into the damages applicable section and drill down into sulfide stress cracking. And in here, we've got some more inputs. So we can say, okay, how much H2S have we got? What's the max Brinell value? Do we have cyanides present? And overall, it comes up with a probability of failure for sulfide stress cracking. Similar thing applies to H2S. And also for CUI, it's a very simple, immediate probability of failure value. So this gives us a overall probability of failure for cracking, so a combined POF of 3. And for external, we have a combined POF of 3 as well. So that all that damage mechanisms and metal loss corrosion rates are carried further forward into our probability section. So in probability now, we have a summary here, which aggregates everything we've just looked at. So we're looking at our metal loss probability of failure at 5, and looking at our cracking at 3 and external at 3. The others are not applicable. So we can see very quickly from the chart where our probability of failure lies, and obviously metal loss being the most probable failure based on the data that we've currently got. So we know about our failures and their probabilities based on our analysis so far. So what is the consequence of these probable failures? Well, here we specify some costs. So based on the equipment that we've selected, RBLX has a data bank of the recommended costs based on the equipment options that you pick. So the recommended cost here is $120,000, and that's what we've put in there. You can specify your own value, but there is a recommendation. Serious injury cost of $5 million here. There's environmental cleanup cost, production impact in terms of percentage of this component failing, and then a weighting between the business and environmental consequence and the safety consequence. So at the moment, we've got 100%. We're looking at business environmental consequences. We're not looking at safety consequences at this point in time. So this gives us a summary below of the safety consequence in dollars, the business consequence in dollars. Obviously, because of our weighting that we applied, we are really looking at that 1,719,817 consequence as a business consequence. And that is indicated by this chart here. So the consequence chart illustrates again the breakdown of the consequence values and looks at the total as well at the end. So now that we have our consequences defined and we have our various probabilities, we can now start to look at risk. So our risk graph looks at the tolerable risk, which is indicated in this green area here. This box that's drawn here gives us our tolerable level. Within that tolerable level, we've worked out a risk for each of these categories. So based on the probability of failure for metal loss and the consequence, we have a risk value here for metal loss. We have the equivalent for cracking as well, and then for external as well. So naturally, they are slightly less than metal loss because of the probability that metal loss had is pushing that value further up a bit. But the graph summarizes quite well our position and the fact that currently we are within the tolerable risk levels at this point in time. However, that is the scene at this point in time. What we want to know is, okay, so we know the risk now, we know we're within the tolerable risk level, but what's going to happen in the years to come, and how should we take our inspection forward to mitigate our risks? So we then move into the inspection plan section. So in here, we've got a matrix which summarizes what we're talking about when we're talking about probability of failure against consequence. So our COF is rated from 1 to 9, and our POF is rated from 1 to 9 as well. So this identifies our risk category, which you'll see on the left-hand side in the table. So this summarization is telling us, for example, we've got metal loss as an overall category. Within that metal loss category, we have a CO2 corrosion rate of 0.35 millimeters per year, and we've got a sour watts corrosion rate of 0.13. That's given us a probability of failure of 5, consequence of failure of 7, between 1 and 9, and that's giving us an overall risk category of medium high. So if you take that COF7 and look on the matrix for probability of 5, you land in that space there. So that's the explanation of where we get a risk category from. Based on the risk category, RBLX will recommend some possible intrusive inspection. So the recommendation is 100% visual inspection UT and non-intrusive inspection, 50% corrosion mapping or profile radiography, and a spot UT. Then taking that recommended inspection methods into account, it then looks at, well, what date should we inspect on? So the proposed inspection date is actually the 1st of February 2018, and why it is that is the following. Remember, our tolerable risk level was 30,000. So when we're going back to our inspection plan, we basically want to test every year going upwards until we reach our tolerable risk, or we've got a maximum of 10 years. We don't let it go any further than that. So in this situation, you can see the risk is slowly rising from 2014 up to 2018, where finally in 2018, the risk has exceeded our tolerable level, and therefore we recommend the inspection to be at that date. Looking at the cracking risk, again, the summarization is there, and we've got the recommended inspection methods. But the risk, as you can see, is never getting anywhere near our tolerable level, and therefore we get the maximum period for inspection, which is 10 years. Applies to external. The risks are slightly higher than that of the cracking one, but again, it only really hits the tolerable level at 2023. So 1 year before the cracking, but a bit longer in comparison to metal loss. So we have good variation there in terms of our recommended inspections and when those inspections should be carried out, qualified by the risk against tolerable risk measures. So the reason behind showing that list is to show you how we actually get to that recommended date. Finally, when all of these components are grouped together and we want to look at it from the perspective of the equipment itself, we end up with an equipment which has a full inspection plan, which you can then go in and identify what the internal inspection date is going to be, and a description of the plan you want to specify. You can do any kind of modifications and formatting to your text here because it's going to finally end up in the report. So you could do bolding, font sizes, underlinings, anything you'd expect to have, alignments, numbering, bullet points, etc. You can specify all this at rich text form. You do the same for external inspection date and the wall thickness inspection date, and then a suitable description would go along with those as well. Finally, the last page of the components for every component. So this equipment currently has only one component, the first stage separator, but if it had multiple components, all of the inspection plans for each of those components would be summarized here, and basically the summarization of what we looked at already. So the metal loss, proposed inspection methods and date, the environment assisted cracking, proposed method, inspection date, and external as well. So we're looking at that in the UI, that's fine, but we want to actually have an output of that. So we click on the equipment report, and that will give us an output in PDF. We can alternatively also save that equipment to our report library, which I'll probably do that just now so we can go and pick it up from there. So when we save it to the, which was the document management area that I mentioned at the beginning of the presentation that we had, what happens is we have the this tags alongside that equipment and the inspection plan document. So you'll see that it was created by me at this day and time. So we can either generate documents from the application, which get stored here as inspection reports, or as you can see here, where Riza has uploaded some other documentation, miscellaneous documentation can be uploaded in here as well as supporting documentation and tagged and grouped appropriately with any kind of tag that you want to have. But this is our formal report here, so we'll just fire that up. So our final report has summarized our internal inspection plan that we manually specified on our date, external and wall thickness as well. Then browsing down, it has outputted our metal loss, proposed inspection methods and date, cracking, and external as well. So basically all the data we looked at before, but we can now print this out as a formal document and output from the system based on all the analysis and calculations and all the data we fed into the system originally. Going back to the component list, if the formal report is fine, that gives us a nice clean report, summary of our risks and our proposed inspections. But actually there's a lot of data behind this. So what if we want to do some further analysis, or we just want to get a good snapshot of all the data? So we can export all the data to Excel, clicking the button at the top there. And this will give me an Excel output of all the data for all the components that we have in the system. So I would save that somewhere on my machine and launch this file. And then we should see in here in Excel a summary of the data. So here we have all the components, and in Excel, all the installation dates, calculation dates, design life, all that data just dumped in there, and there's a whole host of data being extracted from the system. The analysis tabs are then summarized in metal loss. So all our corrosion rates are recorded here. The component specification all the way up to facility, so you know obviously which one it's tagged against. Our cracking, our mechanical, metallurgical, all the probability of failures are recorded here, external and other. Our consequences are all recorded in here. Our risks are recorded in here, and then our final inspection plan dates are recorded in here. So you have a full Excel export of the entire data set should you need that at any point in time. And that concludes my presentation of the software, RBLX, and now open the forum to any questions or queries you guys might have, and myself or Reza will be happy to address them.